The least squares line for the relationship between the number of pounds overweight and the age at death is given as y hat is equal to negative 0.538x plus 63.085. Find the 90% prediction interval for a woman's age at death, given that the woman was 20 pounds overweight. So we're forming a 90% prediction interval, right? For a woman's age at death, given that the woman was 20 pounds overweight. So this problem is really important. It's a 90% prediction interval, not a confidence interval. So we're actually literally trying to predict a woman's death or age at death, given that she's 20 pounds overweight. So it's kind of a shocking problem in that sense. But let's work it out, actually. So the first step that we want to do, since it's a prediction interval, is we want to get a point estimator for the average age for somebody who would be 20 pounds overweight. And so the way we're going to do that is we're going to plug in this 20 pounds into our regression equation and come up with the y hat value. Before we do that, let's go ahead and identify alpha. Alpha is 10% here, right? Or 0.10. Now, the equation for y hat is given as minus 0.538 times x. Now, x is going to be 20 for us. That's our predicting x value, 20 pounds overweight, plus 63.085. Okay, now at that point, let's plug in the numbers into our calculator and get our predicted value, y hat. All right, so we have minus 0.538 times 20 plus 63.085. When you work that out, you end up with the answer 52.325. Okay, so that's your y hat value. Our next step is to take that y hat value and plug it into our equation here. Now, not our equation now, sorry, into our, we're going to use our step 2 to get our table value, T alpha divided by 2. Sorry, I was just actually thinking about this problem a little bit, looking at this model. You know, this is worth mentioning because it's helpful to understand what the model is doing. If you look at it here, it's a negative slope here times x, and that means that, you know, for every pound overweight, you're losing, it looks like 0.5 of a year off of your life, right? Half a year off your life for every pound overweight, according to this model, right? Remember, this model was created from a sample set of data. And what I looked at also that was interesting about this model was that if I were to enter 0 in for x, right, that would cancel out that term altogether. And it would say that the average age is 63. So that would be if they were 0 pounds overweight, you know, they would have an average lifespan of 63 years old. So you can tell here that that average lifespan is, you know, relatively low for this group, because we think that, you know, today the average age for a subject, you know, to live, you know, barring anything else, just a general average is like 87 or something for women. So it's much higher than this 63 value here. And at this point, this model is really only looking at what? Pounds overweight, and then there's this, you know, this number, which is basically supposed to represent 0 pounds overweight, which means that person was the ideal weight, you know, and they're still estimating the average age at that point only to be 63. So there might be something funny about the sample data where this problem came from. But anyways, an interesting model how every pound overweight represents half a year off these people's lives according to this equation. Okay, let's go back to this step 2, which is the table value. And the table value comes from looking up, of course, half of alpha. So in that case, we'll have 0.05. And the corresponding degrees of freedom, degrees of freedom here are going to be 2 from 20, which is 18, right? So n minus 2. Let's go ahead and plug that stuff in. Or, sorry, we'll look at that on our table. So we're going to look at 0.05 on our table and go down to 18 degrees of freedom and see what our critical value is for the problem. Okay, so we're looking for the value 0.05 with 18 degrees of freedom. We find the answer 1.734. Okay, so our critical value is 1.734. Now let's take that now and use it to help us calculate the margin of error. The margin of error is T alpha divided by 2 times S times the square root of 1 plus 1 over n plus the following fraction. Fraction will be xp minus x bar quantity squared over sum of squares for the x's. All right, now our T alpha value is 1.734 times S. S here is 5.3753. 5.3753. Then we'll have that multiplied by the square root It'll be 1 plus 1 over 20, n is 20 here, plus xp, the predicted value, so the prediction value here is 20, minus x bar, which is 8.9 only, square that, and then divide by the sum of square for x's, which is 2,933.8. Okay, let's see what that turns out to be for us. Okay, so we have 1.734 times 5.3753 times the square root of 1 plus 1 divided by 20 plus parentheses 20 minus 8.9, close the bracket, square, divided by 2933.8. Close it up, hit enter, and you get the answer 9.74, etc. 9.7400 ... right? Okay, so that's our margin of error. I'm going to store that in our calculators under the variable x. And let's go ahead and put it to use in our last step, which is filling in the interval y hat minus e, comma y hat plus e. Okay, so y hat is 52.325, right? 52.325 minus 9.74, and then 52.325 plus 9.74. All right, now that'll be 52.325 minus the error, which works out to be 42.58, and then we'll add the error to that, and we get the answer 62.07. Okay, so according to this interval, we are 90% confident that the true age at death for a woman who's 20 pounds overweight will be somewhere between about 42 and a half years to 62 years old. So according to this, again, this is a prediction interval, so we're not saying for the average woman who's 20 pounds overweight. We're saying for this specific woman who's 20 pounds overweight, we predict her age at death to be somewhere between 42 and a half years old up to about 62 years old. So, of course, we're 90% confident of that prediction. So it's a kind of a morbid prediction to make, but that's what we're doing. We're predicting the age that this woman would die, and we're saying it's in that interval. We're 90% confident of that. So again, you know, the problem is a really interesting one, and it's really powerful that we're able to make that prediction with such a high confidence level, just given some sample data and this technique. However, we do want to look at the fact that, as I mentioned earlier in the video, that this number here, which represents when x, if you put x equals 0 into the equation, that's your y-intercept, and that's essentially saying the average age at death for a person who's 0 pounds overweight. If that answer is 63, it seems like there might be something unique about this group of 20 women that they looked at in the study, right, who passed away at some point in their lives, you know, and then they considered their pounds overweight and the problem, you know. At that point, that 63 looks a little low because normally we expect the average life expectancy for a female to be in the upper 80s, and that's a little low. So maybe the data is from an old sample back when the age, you know, the age that people died at was around in the 60s, you know. So if it could have been something from, say, the 50s, maybe there was a time when the life expectancy was around 60s, and so maybe at that point, you know, that was normal for the time that the data came from. But at this point in this problem, I would say that that's a little low. So perhaps this interval might be off just because the sample data might be off. But as far as the result goes, we're still 90% confident. But of course, we know that about 10% of the time we'd be off. So perhaps this interval could be off because maybe the sample data is special or unique. But anyways, it's a very interesting problem and really powerful that we're able to get a result like this just from a small set of sample data and some calculations.